For those of you who may be new to GeoCon, we were founded in 1979 and recognized as the world leader in the manufacture of geotechnical and structural instrumentation. Currently, GeoCon has more than 160 employees, and as of 2022 is 100% employee-owned. Our main headquarters factory, where all our products are made, is located in Lebanon, New Hampshire in the United States. Today's primary speaker will be Jeffrey Barrett. Jeff has over a decade of experience in data management systems and applications. He is a geotechnical engineer who works with our design team to create new hardware and software solutions for GeoCon's various product lines. I'll be acting as secondary speaker and background support. I'm Joelle Lang, GeoCon's training coordinator. I've been with GeoCon for 12 years, and my main role here is to collaborate with our instrumentation experts to deliver training opportunities for those seeking to expand their knowledge. Today's agenda will be covering our tilt monitoring options, both old and new. We'll start off today's presentation with an overview of the recent evolution of tilt sensing, leading up to the technology used in our new tilt products released this past March. After that, we'll discuss calibration factors and specifications before individually reviewing the features and uses of inclinometers, tilt sensors, and tilt loggers. To close our discussion, we'll cover some data management options for the tilt products discussed here today. So from here, I'll go ahead and turn the reins over to Jeff.
Thank you, Joelle. We'll kick off the presentation with a discussion around the different sensing technologies used to measure tilt in the geotechnical and structural applications. So one of the first technologies we saw in the market was a force balance servo accelerometer. And you will hear me use the term accelerometer a few times during this presentation. However, these products aren't used to measure acceleration. We're really just using them to measure static tilt. And that's the case with the force balance servo accelerometer, which is really just a positioning measuring device that has been used primarily in single axis manual inclinometer probes for a number of decades. So this type of sensing technology produce very accurate and precise readings of tilt. However, there were a few drawbacks. The first one was it required frequent calibration. It was not very shock resistant. And the second one was the price of the sensing technology itself, and the fact that it could only be used in typically a single axis format. The next sensing technology used to measure tilt is vibrating wire. Most people would recognize vibrating wire technology for products such as pressure transducers, vibrating wire piezometers, for example, or strain gauges, but we've also developed tilt sensing products around the vibrating wire technology. The figure here shows a single axis tilt sensor, which consists of a pendulous mass and a vibrating wire. And as the sensor tilts, the tension on the vibrating wire changes, and we can read it using traditional vibrating wire sensing technology. There are a number of benefits with this type of technology used for tilt sensing, including low power consumption and low drift. Extremely long cable lengths are permitted, and there's many data logging options. It can also be read dynamically, which is something that is typically not available for the later MEMS technologies. Some of the downsides, however, are it's a single axis sensor only, and it can be relatively expensive when compared to MEMS technology. So moving into the MEMS chips that you will typically find in most modern tilt products. Again, these are MEMS accelerometers, but we're not using them to measure acceleration. There's a whole product line of MEMS chips that are used to measure static tilt that are specifically designed for that application. They offer extreme resistance to shock, upwards of, in some cases, 2,000 to 5,000 G. can get very high resolution, precision, and accuracy, in particular with subsequent in-house calibration. The early MEMS that we saw in the market were typically analog and would output a raw voltage signal, which then needed to be converted into tilt. Most modern tilt products now use either an analog to digital converter on the board, or the MEMS chip itself will include an analog to digital converter, and the output is in tilt in degrees. So typically these products would undergo a calibration to correct things like zero offset and temperature dependent uncertainty. I'll get into that a bit later. And one of the major advantages to these products is not only that they're a small footprint, but they're a small footprint and can be 1, 2, or 3 axis capable. So the operation of the MEMS accelerometer is actually quite similar to the servo-based accelerometer in the sense that there's a mass supported between 2 springs, and really we're measuring the position against a fixed reference. Again, these are used to measure static tilt, not vibration or acceleration. There are very specific MEMS chips that would be used for those types of measurements. Typically, the sensor is read many times, perhaps 100 or 1,000, and an average reading is calculated using a microprocessor on the board, and that single average reading is sent via typically RS-45 communication protocol to a data logging system. So one of the things that we typically get into when we're discussing these types of products with potential clients is how accurate are the readings. The accuracy requirements will depend on the type of application, whether it's a downhole geotechnical application where maybe tens of centimeters, or in some cases 1 meter of movement might be expected, all the way up to structural applications where fractions of a millimeter may be required to be measured. So these are some of the terms that we typically come across when talking about the kind of generalized term of accuracy, right? So we have terms like precision, resolution, sensitivity, nonlinearity, temperature dependent uncertainty, repeatability, and sensor noise. And these different terms are sometimes used interchangeably and in some cases incorrectly. So it's important to understand what each of these terms means and how the value that's on the manufacturer specification sheet will impact the quality of data that you get on your specific application. So this is a relatively common figure that has been used in many applications to describe accuracy and precision, but just thought I would go through it quickly. So the top left, you have accurate and precise. So not only are the points closely grouped together, they're on target. So if you think about a tilt sensing application, it's measuring the actual angle with a high level of repeatability across different reading intervals. So the next one going down is precise but not accurate, and I would say this is perhaps where the typical MEMS sensors would fall, where the actual angle of tilt may not be as accurate as it is precise. And a lot of times that doesn't matter because people are typically concerned with the change in tilt and not so much the absolute angle of tilt. And then you have the other two, accurate, not precise, and neither accurate nor precise. So I thought I would take some time to go through a typical tilt product specification sheet. So this is for one of Geocon's tilt products here. So the first spec item is range, and this essentially just is a description of the appropriate range that would give output from the sensor. So this is different from the calibration range, of course, but if the sensor is within plus or minus 90 degrees, you will be able to get a reading. The next item is resolution, and you can see that this is a very small number at plus or minus 0.004 millimeters per meter. With the modern digital MEMS chips, the resolution is typically much higher than is really required, and is actually just a function of the number of significant figures that are kept throughout the data processing phase of taking a reading from the sensor. So, you know, this is really a meaningless number when you're looking at quality of data for tilt products, and you really just need to see that that number is better than the precision value. So moving on to precision value, this is really the repeatability of a number of sensors. So this is typically given with a confidence interval, perhaps 99% confidence interval, and the test to come up with this value would need to be done across many sensors, perhaps 100 or a couple of hundred sensors. The next one is nonlinearity, and this really talks about the error associated with the calibrated range. So here we're talking about a nonlinearity across a plus minus 30 degree range. The next value is temperature dependent uncertainty. And I would say this is probably one of the most important spec values for above ground tilt sensors. So if you are talking about a downhole sensor, an IPI that is tens of meters below ground, you might not expect there to be much temperature change throughout the life of the sensor. However, if you have a surface mounted sensor, you would expect a very large temperature swing throughout different readings, both seasonally and daily. So we've specified this parameter across 3 different ranges. So the closer to vertical the sensor is installed, the better the temperature dependent uncertainty. So every manufacturer would typically do their own temperature correction and would have different algorithms and proprietary ways of correcting that. And for our calibration process, we've decided to present the specification in 3 different ranges. And then of course you have operating temperature and the accuracy of the temperature sensor itself. So what does all that mean? What I've shown here on the right-hand side is a plot of an IPI that is installed in a casing in the field, in bedrock, where the customer knew that there was little to no movement occurring. So this is a fairly stable environment, and we use this to validate the performance of our IPI against the specification. So the specification is derived from the sensor itself. When you talk about the actual performance of a product in the field, you're talking about system performance, not sensor performance. So what you see here is a collection of 20,000 readings for an IPI where we deemed there to be no movement. So we're really looking at the precision of this particular sensor across 20,000 samples. The sensor precision that we've put on our specification sheet is plus or minus 0.13 millimeters per meter, and that's at a 99% confidence interval. So what we would want to see with this type of test is 99% of the data should fall within that plus or minus 0.13 millimeter per meter, and you can see we're well within that range. The other thing that we can show here is resolution, and I've shown in the bottom, the resolution value. So this is the smallest change in angle that you can detect. So you can see here when you're talking about the resolution value, it's really meaningless when you have a precision value here that is, much, much larger. I'd like to talk just briefly about the temperature-dependent uncertainty. This is a plot showing temperature on the top line here, where you can see very large swings of, perhaps up to 20 degrees Celsius per day. And this is a MEMS sensor without temperature correction. So you can see the cyclical data that you get that's following the temperature change, and this can be fairly significant, depending on the level of movement that you're trying to detect on a structure. I did speak about the temperature dependent uncertainty and the impact on angle. So we would want to try to orientate the sensor close to vertical. So this is an application where a sensor was placed on the face of a dam, and a specific housing was designed to keep the sensor close to vertical to optimize that specification parameter. So at this time, I will get into the new tilt products designed and manufactured by Geocon. The first one is the 6180 in-place inclinometer. This product has actually been available for a number of years now. It includes the latest MEMS chip technology. This is a 3-axis sensor. The housing is constructed with 316 stainless steel and an engineered polymer, which is ideal for marine or corrosive environments. Spent a lot of time optimizing the design to reduce weight. It's 50% lighter than previous IPI. We've also gone with a tool-free connection. So you can see on the second photo, the ball and socket connection that is easily connected by hand without any subsequent tools. And then finally, the sensor cable connection, which is fully waterproof and rated to a pressure of 300 meters of head in water. So some more data from the field trial that we did on these IPIs here. You can see here some in-place inclinometer data collected over time, and the gray error bars, which are the accumulated error from bottom to top. This error includes resolution, precision, nonlinearity, and temperature-dependent uncertainty, which is seen more drastically at the top. So you can see, because the error bar is cumulative, you would expect the error at surface to be larger, and then the slope of this line creates an even larger error at the top because of the temperature change at the top of the hole compared to the temperature change that you might see midway or at the bottom of the hole. So we always recommend, whenever looking at, in particular, inclinometer data where the errors are cumulative, to plot the error bars alongside the data to ensure that the perceived movement you're seeing is in fact actual movement and not perceived movement associated with the error of the instrument. So the in-place inclinometers are installed in a groove casing, any typical inclinometer casing. We prefer the groove casing to maintain azimuth of the string from bottom to top. Because these are in fact triaxial sensors, we can measure both the A and B axes with a single chip. Typically, the A-axis or the wheels are orientated in the direction of anticipated movement. This is a typical installation project done by one of our partners, where several hundred IPI casings or inclinometer casings were instrumented with 3-meter IPIs. We also offer a combined product with the Geocon 6180 IPI paired with the IPX magnetic extensometer, where the magnetic extensometer is connected to the B-axis of the IPI and allows for measurement of tilt and settlement of the casing using a single borehole. Moving over to the horizontal IPI, this product is very similar to the vertical IPI, with the only difference being we calibrate all 3 axes with the horizontal IPI, and we have a rigid connection at one end to maintain constant spacing from the end of the casing. This utilizes the same 316 stainless steel engineered polymer and is available in standard lengths of 0.5 meter, 1, 2, and 3 meter, 2 foot, 5 foot, and 10 foot gauge lengths. And of course, you can mix and match these gauge lengths throughout a single string to optimize cost and spatial resolution of the data collected. The next product is the triaxial tilt sensor. Again, this was designed to make use of similar components as the 6180 IPI. It's typically provided in a single length of 10 inches and is 3-axis calibrated. One of the benefits here compared to some other tilt sensors that you see in enclosures is that it is waterproof to 300 meters as well. So for any marine applications or below water applications, this is a really good option. All of these tilt products work on an addressable bus. So through connect cables, you can connect a string of these sensors together and connect them to a single data logger. This is a project by one of our partners in Northern Canada, doing some temporary monitoring of a bridge pier during construction. So you can see in this particular installation, there are 2 tilt sensors connected to a single data logger. And in this case, it's a satellite data logger, as there was not cell reception available on site. And the final tilt product I'll review is the Triaxial Tilt Beam. So this, as you can see, is also a very similar design as the IPI, with 7 standard lengths, although we can obviously do custom lengths as well. And this, similarly to the horizontal IPI, is calibrated for 3-axis. So there's flexibility in mounting orientation depending on what you're looking to monitor. So these are some typical graphics to show installation. The same product can be installed vertically as well as horizontally and connected with our interconnect waterproof cables. And in some cases, like we've shown here, they're installed in pairs with a vertical and horizontal tilt beam installed in a single location. So this particular project is a monitoring project carried out by one of our clients, Monitor Precision Monitoring in Toronto. And in this case, there's a number of concrete panels where they're monitoring tilt with the vertically installed beam and differential settlement between the two panels using the horizontal installed beam. These are installed in several pairs throughout this underground corridor, and then a single cable is run up to surface, and in this case connected to a SenseMetrics thread, and the data is streamed to the SenseMetrics platform to utilize their full suite of visualization and alarming and reporting tools. So there's several data path options for all of these tilt products. They are all addressable, so really any logging solution that supports Modbus communication protocol can read these sensors. We would typically look to a high power logging solution like a Campbell Scientific based logger for very long strings in order to provide enough power to the bus to read all of the sensors. We also have GeoNet addressable or digital nodes, which can read up to 32 sensors on battery, or up to 60 on internal battery, or up to 62 sensors on external battery. And then we have a number of cloud connected solutions to stream the data directly to the cloud as well. So we'll go through some of the data logging solutions that are used for the addressable tilt products, as well as some of the what I call tilt in the box products as well. So this is an overview of the GeoNet product line. So this digital node that you see here would be used with any of the addressable tilt products. They can be configured with a variety of telemetry options, including radio, cellular, Wi-Fi, and satellite. So these would be used to read a large number of tilt sensors. We also have a tilt node or tilt logger, which has a 3-axis calibrated MEMS included in the enclosure itself. And again, these are available with all of the telemetry options that we have with the GeoNet product line. So I mentioned the addressable logger. This is a relatively small footprint. We can operate these on 2 D-cell batteries and support up to 32 IPIs with those D-cell batteries, or up to 62 with external solar power. Those D-cell batteries, battery life is up to perhaps 2 years, depending on the configuration of the network and how frequently readings are taken. And then the tilt loggers that we have, so tilt in the box, we're measuring 2 axes at a time. They can be available with 3 calibrated axes, but really with any of these 3D products, you're only measuring 2 axes at a time. We have different mounting options available depending on the application, and again, battery life depends on configuration of the network. So final installation case study here. This was a project that we did with one of our partners in Asia, where the client required monitoring of several retaining wall structures across the city, and it was decided to go with the cellular tilt products because of the long distance between the different loggers. That really made the wireless mesh unattractive because of the number of gateways that would be required. So this is a great way to have a standalone system that measures tilt It's really low to zero maintenance with the 10-watt solar panel constantly recharging the battery and the data streaming directly to the cloud. In this case, there was a subsequent protective enclosure put over the logger just to protect it from minor debris that could potentially come down off the side of the retaining wall. So with that, I'll pass it over to Joelle to go through any of the questions that we received in the chat.
We don't have any questions in the chat. We could give it a minute. If anybody has any questions on any of the material that Jeff just went over, go ahead and type that in now. While we're kind of waiting on that, why don't you go ahead to the next slide, Jeff, and I'll just talk over Teams and communication.
Sure.
So if you are interested in learning more about any of the tilt monitoring options discussed here, or you'd like to contact us about pricing or to discuss any kind of project, these are our teams that can help. Sales can assist you with an initial consultation, as well as provide pricing and support through the sales process. Our technical support group offers installation, configuration, and troubleshooting support for new and seasoned users. Or if you're looking for any kind of training for personnel before going out into the field and getting your hands on some new instruments, our training team can assist in setting up custom training sessions on product hardware installation or software configuration. We will also be hosting some in-person training here in June, so check out our Inclinometer immersion course on our website if you'd like to find any more information on that. A question did come through in the chat asking if the presentation will be available. Yes, we will be posting the recording of this presentation once we're done here. That should be available on the website within the next business day. And I'm not seeing any other, oh. All right, Jeff, we have a question. Jeff?
Yeah, sorry, I can't see the question. Maybe you can read it for me.
Oh, no, that's okay. Sorry. When reinstalling vertical IPIs, do they have to be, does the baseline have to be reestablished each time?
Yes, it's always recommended when you are reinstalling IPIs to re-baseline. In a perfect world, you would be able to position the segments in the exact same position. However, that's rarely the case, and there's typically an offset associated with reinstallation of IPIs. So it's always good to re-baseline when you do a reinstallation.
What tips or advice do you have with respect to deploying wireless data logging systems in the field?
Sure. So I think there's a number of different wireless systems, from various different manufacturers, and they're all slightly different. They all have benefits and challenges with the installation and operation of these systems. So one of the things that I would recommend is really make sure that your team is well versed in these wireless systems, how they operate, and the limitations. One of the unfortunate terms that a lot of people have used in this industry is this plug and play term, and I really don't think that's an appropriate term for these types of systems. Although they are significantly easier than data acquisition systems of 15 or 20 years ago, they still require well-trained individuals to deploy them And there's also an ongoing maintenance requirement to these systems, not only from a power standpoint to make sure that batteries are changed, but also as the project environment changes, you may find that a wireless network that was originally configured for a site will no longer work a year or two later after the site has changed significantly. So I just think that you really need to educate yourselves about the types of products available. Um, there's no one solution that's the best for every project. I think it's the onus is on the individual monitoring contractor to really evaluate the technology that's available and choose the appropriate technology for that specific project.
How much drift can we expect from a MEMS inclinometer over the course of 5 years?
That really depends on the type of MEMS sensor that is used. The modern digital MEMS sensors, I would say, are generally zero drift, or the drift that you would see over 5 years would be negligible compared to the precision of the system. That being said, not all MEMS are created equally, and there are some of the older MEMS sensors that did experience drift over time, and there are ways to correct for that. But it's important to know the type of MEMS sensor that's used in the geotechnical sensor that you're using, and understanding specifically what the drift is for that sensor and how it may impact your readings.
What type of lightning protection, if any, is recommended for these products discussed?
Lightning protection is really a site-specific design. We obviously, if you have a data logger out in a field that's prone to lightning strikes, you'll want to ground that. It's really based on your local conditions and what type of logging solution you're using, and what grounding options are available for that. But they're fairly expensive sensors, so for the additional cost of appropriate grounding, it's always something that we recommend our clients install.
How frequently do MEMS devices need to be sent in for recalibration?
So typically recalibration is not required for modern MEMS devices. In some cases where if a customer is worried that a sensor was damaged, we could check the calibration, or we also see that there are some specifications that perhaps were carried over from the old servo-based accelerometers that require instruments to be calibrated every year, every 2 years, and we can do that recalibration, or really what it is a calibration check or validation, but typically it's not required to calibrate modern digital MEMS.
Given all the advances in MEMS technology, is there still a place for vibrating wire tilt meters?
Yeah, so there are a number of applications where vibrating wire tilt meters may be more appropriate. One of the instances that we see is long cable lengths and flexibility of data logging solutions. So because modern MEMS devices use RS-485 and Modbus communication protocol, every manufacturer will have their own proprietary way to communicate with the sensor. So if for flexibility of data logging solutions, the vibrating wire tilt sensors are nice, because any vibrating wire logger readout unit can read those sensors. So there's definitely still, some applications where they may be preferred.
Great. All right, that is all the questions that we had. So we will go ahead and conclude today's webinar. Thank you everybody who attended. We hope that you enjoyed this presentation. Please feel free to reach out at any point to discuss any of these products with us any further. And we hope you have a good evening, afternoon, or morning, depending on where you may be. Thank you and goodbye.
Thanks, everyone.